Hello everybody, welcome back to Glaciers and Glacial Geomorphology. Today we're talking about glacier hydrology and meltwater. That's going to take us over a couple of videos, and in this first one we're just talking about water in glaciers. So in this first video of the pair, we're going to have an overview of where water exists in glaciers, what it does. We're going to specifically mention basal hydraulic systems. Water at the bed of the glacier is particularly important in the context of what we're covering in this module. And we're going to remind ourselves a little bit about some of the links between glacier hydrology and ice dynamics that we have talked about previously, but I really want to emphasize them again now in the context of water in glaciers as a specific topic. Then in the next video, we'll say a little bit about meltwater and meltwater regimes, particularly thinking about the proglacial impacts of meltwater, which includes fluvio-glacial geomorphology, landforms and landscapes which reflect and preserve the effects of water from glacial systems in post-glacial landscapes. And that will lead us through into the final third of the module, the final section of the module, where we're going to be focusing on geomorphology. So for this video, it's an overview of water in glaciers. This image from Bennett and Glacier's 2009 textbook Glacial Geology illustrates quite nicely one of the things I often say to students, that at the large scale, if you can imagine water existing somewhere within a glacier, then it probably does in some glacier. Certainly in temperate glaciers, where the ice is at or close to the melting point, there's water all through the glacier system. In this diagram, for example, which illustrates what's going on at the large scale, there's potentially water within the snow and fern in the accumulation area. There's water in crevasses in that part of the system. There's water flowing end-glacially, either held in pockets or flowing through conduits, water in crevasses again, coming down through the accumulation, from the accumulation zone past the ELA down into the ablation zone. Then we may well have supraglacial water in channels or in ponds on the glacier surface. This supraglacial water may flow all the way to the surface and exit the glacier supraglacially, or more often it penetrates into the glacier, into the end glacial zone through crevasses or through moulins that get the water end glacial, from where it maybe reaches the base and flows as basal meltwater. In a permeable substrate, the water can then enter into the substrate. If we have impermeable bedrock, then it's going to be confined at the basal layer here, and then exits as meltwater into the proglacial environment. So at the grand scale, there's water supraglacially, end glacially, and at the base or subglacially, and potentially within the substrate. So water can be effective throughout the glacier system. Now that's illustrating what's going on at the big scale. We can also see water at the small scale, and these diagrams just come from the 1999 Glaciers textbook from me, but it illustrates how water can exist right down at the ice grain scale and at the scale of the vein net. So in the top part of the diagram here, we have a view of theoretical ice crystals, and you can see I've drawn water at the boundaries between these crystals, both narrow water films at the 2-grain boundaries, but also water in the vein network at the 3-grain boundaries, which is illustrated more clearly in the bottom diagram there. But I've also got water in figures within the crystals and around air bubbles inside the crystals. So even at the crystal scale, water can exist at a very small scale, at the micro scale, within and between ice crystals within the glacier. So these three pictures, all taken from the western margin of the Greenland ice sheet, just above the Arctic Circle, on or around the Russell Glacier. They illustrate these three zones, if you like, or these three territories within which we can think about water in glaciers affecting the glacier system in different ways. On the left hand side here we have the supraglacial environment, and you can just about pick out here some supraglacial meltwater ponds and some channels, streams flowing over the glacier surface. We can think about the end glacial and subglacial water flow, and here you can see water emerging from underneath the Greenland ice sheet. Interesting, here you can just about pick out that the water is freezing as it emerges, because it's cold on the outside of the glacier. The temperature here is below the freezing point, but underneath the glacier we have a warmer thermal regime, and water is emerging as liquid but then freezing as it emerges out into the proglacial environment. And the proglacial environment, well, that's the third realm, if you like, that we want to be thinking about how meltwater is active within glacier systems, and that's one that we'll come on and look at a little bit more in the next video. But for this session I want to think about supraglacial, endglacial and subglacial water in particular. So let's think first of all about the supraglacial environment, and this again is Greenland. You can see on the map in the top left hand corner, this is a map, and it's a bit of an old one now, but you can easily find newer versions of this to get up-to-date information. And this is a map showing where ablation is happening on the surface of the Greenland ice sheet, and the different colours represent the number of days per year when ablation occurs. So right in the middle of the ice sheet, certainly about when this data came from, there was little or no melting right in the centre of the ice sheet in the middle of the accumulation zone, but then all around the edges of the ice sheet in the ablation zone there were many days per year where melting was occurring. That melting generates meltwater. Well, where does that meltwater go? Well, zooming in here, and we're actually zooming in into this area here again around about just above the Arctic Circle on the west coast of Greenland, and zooming into that in a bit of detail, you can see here an interior zone where the ice sheet is covered in snow. If there is melting going on there, the meltwater is percolating into the snow. It's held within the snow, and you can't actually see it on this satellite image. But as we move towards the margin and we're losing our snow, moving into the ablation zone where there's bare ice at the surface, you can begin to see here, and let's zoom in on that, you can see here supraglacial meltwater existing in ponds on the glacier surface, and some of these ponds you can pick out on here are connected by meltwater channels. So there's a very prominent supraglacial meltwater system in that area of the ice sheet, in between the zone in the interior where you can't see any meltwater, then also the zone towards the edge here where you're not seeing so much surface meltwater. So what's going on there? If there's surface meltwater here, how come that isn't being carried on the glacier surface all the way to the edge and existing in this area as well? How come there's just almost like a strip of ice where there's meltwater on top, and that disappears as you move out towards the edge of the glacier? Well, the clue here is in this figure again from the old 1999 textbook that shows how supraglacial drainage networks don't necessarily flow all the way to the edge of the glacier, but they terminate in access points such as this one, a moulin here, where meltwater flows across the surface, then finds an access point into the interior of the glacier. And because it's more possible to access the interior of the glacier and get in end glacial as you move towards the glacier margin, crevasses open up, perhaps you're dealing with warmer ice so that the water can penetrate more effectively into the interior of the ice without freezing. But for a variety of reasons, as you move towards the margin of the glacier, we're more able to get water from the surface into the interior. And these pictures that I took on the surface of the ice sheet in that location, right close to the margin, just illustrate for you how difficult, just in a common sense kind of way, you can see it would be quite difficult to keep water at the glacier surface because the glacier surface is so fractured, crevassed, and these crevasses penetrate deep into the ice. So if there were meltwater at the surface here, it would be able to penetrate into the interior. In the one picture on the top right here, where you can see me kind of straddling that crevasse, there is actually a little bit of frozen meltwater in the bottom of that crevasse, but you can see in the back of the distance behind me, the crevasse has opened up much more significantly, and any water back there will have penetrated down into the interior of the glacier. And here you can see we're quite close to the margin, so the ice here is relatively thin, so it wouldn't be that difficult for crevasses to penetrate very close to the bed, and for meltwater therefore to also penetrate through the ice and down towards the glacier bed. I keep using that word moulin, and I showed you the little map earlier, and you can see that in the textbook where the supraglacial drainage networks end abruptly, a little point where they just disappear into the ice. So this is a photo from Wikimedia Commons of a moulin on Snowbird Glacier in Alaska. And this just shows the situation that I was talking about. So there's a figure there for scale, person for scale. And you can see we're looking up glacier, and water, supraglacial meltwater flowing at the surface of the glacier encounters this access point and drops down. It's like a sinkhole in karst terrain. And it might not, well, it won't have always been such a big hole. It'll have been a small point where water can penetrate, maybe an access point through a crevasse or something like that, but a small access point that will have been widened by erosion and melting by the meltwater, and also potentially by sunlight getting into the top and widening the access at the top of the hole there. But a moulin is a way for surface water to penetrate into the interior of the glacier and potentially down towards the bed. And that's the next stage of our journey, if you like, thinking about water at the bed of the glacier. And in the bottom right here, here's a picture of a former Kiel student walking through a tunnel which has been excavated by meltwater at the base of a glacier in Greenland. And here's me standing in front of the glacier Solheimjökull many years ago, when it was far advanced of its current position. And again, we have a tunnel emerging from the ice, or a tunnel going into the ice through which glacial meltwater is emerging. So evidence here of water flowing at the glacier bed and emerging from the glacier into the proglacial environment. Let's look at that in just a little bit more detail. So again, these are just a couple of diagrams from the basic old textbook. And the top diagram here is just illustrating the different ways in which water can be stored or can travel at the glacier bed. And I've divided it up into the three main sections. First of all, film flow, the idea that if ice is resting on bedrock, there can be a very thin film of water between the ice and the bed. And when we say film, we're not even talking centimeters, we're talking often a micron's thick film of water. So it's just a wetness, if you like, between the ice and the bed in temperate glaciers. At a bigger scale, we can think about water flowing in channels or tunnels, and then we can also think of water being stored in cavities. And here you can see ice motion is from left to right across the slide. So I've drawn a cavity on the downstream side of this obstacle. So you can be almost thinking back here to what we were talking about with regelation and so on, where ice is flowing around obstacles, and if the ice is moving quickly enough, it's not going to retain contact with the obstacle on the downstream side, but a cavity will open up. And these can be air-filled cavities, but they can also be water-filled cavities. And you'll remember that when we've talked about surging, and you remember we talked about we started talking about that CAM 1987 paper and more recent papers about surging and water flow at the glacier bed affecting glacier dynamics. Well, those talk about the linked cavity system. Well, here's your cavity, and here are some of the potential linkages between them, and here's your next cavity. So when you think about a linked cavity system, here's your cavity, here are the links, but it might even just be film flow linking water from one cavity within a network to water in the next cavity. Now, the channels or tunnels are often spoken about of two different types: N for John Nye and R for Hans Roethlisberger. So they're named after well-known glaciologists who did work on this topic. But tunnels or channels at the bottom of a glacier typically take one of these two forms. A Nye channel, you can see what I've drawn here, is ice, the ice bed at that level, and here's the bedrock, and the channel is cut into the substrate. So the bottom of the ice is flat, the channel is cut into the substrate. And if you imagine removing the glacier here, you would be left with that channel still cut. If this is bedrock and can be preserved into the future, then you'll have the Nye channel still cut into that bedrock after the glacier has gone. By contrast, the R channel, the Roethlisberger channel, that's carved upwards into the roof, if you like, or into the ice. So here the bed of the glacier isn't particularly affected by that water flow. Water will be flowing within this channel cut up into the glacier. In all these situations, the ice will be trying to close that gap. Remember Glen's flow law, etc., and remember you have an overburden pressure. So the ice will be trying to fill these gaps. The ice will be trying to close this tunnel, and the closure of that tunnel, or its remaining open, will depend on the ice pressure, the overburden pressure, versus the water pressure within the tunnel, forcing it open. If it's full of water under pressure, then the water pressure itself can keep the tunnel open against a certain overburden pressure from the ice. And also by melting or erosion of the tunnel, including thermal erosion, but melting or erosion of the ice by the water flowing through that channel. So if lots of water is flowing through, that will help to keep it open. So we're going to talk in a second about the seasonal evolution of drainage networks. And already now you might just be thinking a little bit about that and thinking, well, okay, so in the summer, in the spring and summer and autumn, there's going to be lots of meltwater flowing around, so that will help to create these channels and to keep them open. But what happens in the winter when there isn't so much meltwater being produced? If you don't have meltwater going through those channels, and if the ice overburden is trying to shut them, there's no water to compensate. So do the channels tend to close in the winter and be reopened in the spring? Maybe that's something you're thinking about. We'll hold that thought and we'll come back to that, but certainly apply that kind of thinking also to what we've said about glacier surges in the past, and think about the seasonal evolution of glacier dynamics based on the seasonal evolution of glacier hydrology, and hopefully that will begin to put together a kind of a picture in your mind as to how these things hang together. Well, this is just to make another connection or tie up another loose end, if you like, between things we've talked about previously and things that we now just need to mention once more as we're talking about glacier hydrology. This is an upwelling of glacial meltwater in front of a glacier in southern Iceland. I think this is Skeiðarjökull, and that's me standing at a supercooled upwelling. So do you remember we talked about glaciohydraulic supercooling and the idea that water, even in a temperate glacier, water could be below zero, below the atmospheric pressure freezing point, if it's at high pressure in a subglacial overdeepening. And as water emerges from that overdeepening, if the geometry of the overdeepening and the geometry of the glacier surface is correct, it can emerge up the adverse slope. It can emerge from the glacier below the freezing point, freezing as it goes, or if it hasn't frozen by the point that as it emerges up that slope, if it hasn't frozen to create a basal ice layer as it's coming out of the glacier, then as it emerges into the ambient pressure of atmospheric pressure, it can freeze to create these frazzle ice or anchor ice features. So supercooling leading to freezing of water as it emerges from the glacier. And this is a little terrace essentially created by frazzle ice. If it's stuck to the ground, if it's stuck to the rocks underneath, we call it anchor ice. If it's floating fragments of ice like slush, we call it frazzle ice. And this is ice created around one of these outwelling vents where water is emerging, freezing as it emerges, and building up this rim of ice through which the emerging water then has to escape. Just from a health and safety point of view, I should say that if you're going to go and stand in supercooled water, you probably shouldn't just be wearing tennis shoes. That's not the recommended practice. I don't know what I was thinking. Okay, so we've seen so far that water exists in all sorts of different positions within a glacier: supraglacial, englacial, proglacial, at the big scale, large volumes of water, also at the micro scale within ice crystals, for example, microscopic amounts of water. The next question to move on to is, well, what effect does that have? And here, as in the previous section, don't think I'm going into all the details. Remember to do the backup reading as well to add some detailed information to this signposting that I'm trying to give you in these sessions. So what effect does the water have? Well, we can think about the effects of glacial meltwater at a range of different scales, and we can think of it impacting in a variety of different ways. I'll just move myself out of the way here so you can see all the pictures. So here, for example, again, West Greenland, and you can see one of the grand scale processes that we're interested in this module: sediment transfer from the glacial part of the system through the proglacial and into the oceanic part of the global sediment transfer system. Well, meltwater is really important, a really important part of doing that job of moving sediment, moving earth surface materials through these systems. Also, we can think about the impact on the glacier margin. So here, for example, we have a an ice terminus which is floating in water. Well, you remember when we were talking about glacier fluctuations? Glacier fluctuations and their response to climate change very much depends whether you have a floating or a land-based glacier terminus. So water at the glacier margin can have a big impact on glacier fluctuations. Earlier in the module we talked about the basal ice layer, and we talked about how basal thermal regime affected the availability of water and so on for refreezing water to generate basal ice. And also we talked about this dispersed facies that you can see in the bottom left hand corner there, and we talked about a variety of theories for the way in which dispersed facies ice might be created. Some people think it's by the freezing of bulk amounts of water underneath an ice sheet. Other people, including myself, have suggested that it's all to do with the flow of water through the vein network. It's a metamorphic effect where you get partial melting, partial refreezing, and flow of water and debris through the vein network. But whatever's going on there, it appears that water, perhaps at that micro scale, is really important in the generation of that basal ice. And here in the bottom right, we've got the air photo of the variegated glacier, which is one of the glaciers that you're very familiar with now from having talked about glacier surging. It's a rigid bed surging glacier. And when we think about the likely mechanisms of surging in a situation like that, well, basal water pressure, changing basal water systems, seasonal and long-term evolution of the subglacial drainage network, those are the kinds of topics that jump up at us when we start trying to explain how glaciers surge. So lots of examples there of ways in which meltwater is really important, or water in glaciers is really important in a variety of different contexts. But I've put in the caption here, I've specified ice dynamics, because in the context of what we've been talking about throughout this module, it's that impact of water on glacier dynamics which is really central to a lot of different things that we've been talking about. And that's going to also remain important as we move forward and start talking about geomorphology. Now, we also need to be aware, and this is what we're moving on to over the next few weeks, of the geomorphic impacts of water in glacier systems. Glacial geomorphology is partly to do with ice impacting the landscape. It's partly to do with ice impacting the landscape in different ways because of the way that water is controlling the behavior of ice, and it's to do with water within a glacial system impacting the landscape itself. So we have both direct impacts of water in glacier systems on the landscape and indirect impacts of water on landscapes through its impact on ice dynamics. So lots of different things to think about when we're talking about glacier meltwater and geomorphology. And these photos, just to kind of throw up a few topics for you to be thinking about and maybe in following up in your reading. This top left-hand photo is a picture from the channeled scablands in the northwest part of the USA. The channeled scablands being where meltwater from the Missoula floods escaped, or lake water from glacial Lake Missoula flooded across the countryside, creating huge scale geomorphic features associated with that glacial meltwater escape. In the top right, that's a sander plain, a glacial meltwater outlet stream heading from Russell Glacier in West Greenland, heading out towards the fjord. This is part of that same glacier meltwater system, and I stuck this photo in to illustrate how river channels in these environments are very largely a response to the characteristic of the river channel. The fluvial geomorphology is a response to fluvial characteristics that are determined by the glacier system. So here, for example, in Greenland, we have very variable water discharge between summer and winter, lots of water in the summer, none in the winter. We also have periodic large floods from releases of meltwater from the glacier, and we have a lot of sediment available. And that combination of variable water discharge and high sediment availability, that leads to a very particular type of channel geomorphology and a very particular type of channel sedimentology. So even if you didn't know that this was a river in a glacial system, looking at the morphology and sedimentology of the channel would give you very strong clues that there was a glacier upstream of here. And that's one of the nice illustrations of connectivity between glaciers and their surrounding environments. The characteristics of the proglacial environment depend to some extent on the characteristics of the glacial environment that lie behind them. And the fourth picture in the bottom left, that's a photograph of a bunch of students, in fact, walking through the landscape near Kiel. If you head out through Kiel village and then across country along the footpaths to the village of Madeley, you'll follow this route. And your route there is through the bed of former glacial Lake Madeley. And the landscape around Kiel, a very typical middle of England landscape that most people wouldn't look at and think, oh yeah, glaciers made that. It's created by glaciers, but particularly by glacial meltwater, and a lot of the topography around our university campus relates to glacial meltwater effects, either meltwater channels or infilled glacial lakes, and there's even a little glacial shoreline. You can't really pick it out very well on the photo, but if you go and have a little bit of a walk around glacial Lake Madeley, you can actually find ancient shorelines on the hillsides, and then different sediments down in the base of what used to be the lake, the sand and silt, bits of clay, but mainly sand in the base of the lake, and then glacial till up around the sides of the lake. So lots of different geomorphic impacts of meltwater, as well as the ice dynamic impacts that we've talked about previously. Just as an excuse to give you some more photographs of glaciers, another impact of meltwater on glaciers can be an impact on the morphology or the shape of the ice margin. So these three photos are all of actually pretty much exactly the same location at the front of the Russell Glacier, but at different times of year. And there's something like a 60 or 70 metre cliff at the front of the glacier here, which is maintained by a stream flowing across the front of the glacier. The glacier is advancing up a slope, so the terrestrial surface water in this area is held back against the glacier. It doesn't flow away from the glacier, but runs along the front of it, undercutting, causing massive avalanches and calving. But then at different times of year, there's more or less water in here, and so the ice is more or less able to move forward a bit, or not move forward so much, or it's being undercut, or it's not being undercut. And here's a photo at a slightly different time of year where the ice cliff isn't quite so prominent. And then this section down here, at some times of year, there is no ice cliff, and that little black dot there, that's actually me standing at the front of the glacier, standing on what's left of this proglacial river when it's frozen over in the winter. And the morphology of the ice margin is very different now, because ice blocks carving off the front of the glacier, or as the glacier moves forward, it isn't being eroded away by the stream. So if this stream hadn't been here, the whole front of the glacier would have had this typical glacier front lobe profile. But because there is a river flowing across the front of the glacier for a large part of the year at least, that river holds the glacier back by eroding off the front, and where we have this 70 metre cliff, it's essentially a cross section through the front of the glacier, because the very frontal bit is being removed. And here's one more illustration of meltwater effects at the margin of a glacier. This is a sequence of photos taken at the front of Solheimjökull Glacier in southern Iceland many years ago. And there, for scale, there's me standing at this portal where meltwater from underneath the glacier is emerging. And then over the course of several weeks, you can see what I was talking about previously about the tunnel roof. This is an R channel essentially emerging at the glacier margin, and you can see that tunnel roof being closed by the overburden pressure of the ice, and you can see fractures in it. You can see a slight asymmetry in the tunnel here. We're kind of up against a valley side on this side of the photograph, but you can see over the course of time the morphology of that tunnel changing to the point where this ice block here collapses into the river and blocks the tunnel. And an interesting hydrological effect occurred here. Damien Lawler wrote a paper about this, talking about the heartbeat effect in the discharge of this stream, because the stream discharge coming through quite happily then gets blocked by these ice falls, and temporarily no water is emerging from here, so that the tunnel is blocked. Water builds up in the tunnel, so the discharge of the stream is lower at this point, and then at some point the water manages to break its way through and demolish that dam. All of the stored water is released, leading to a peak, in a short-lived peak in discharge, and then the discharge returns to normal. So you can draw it with the cursor here. You can imagine a discharge curve where the water is flowing through normally, then the discharge drops because of the the blockage, then the discharge rises again as the stored water is released, and then the discharge returns back to normal. So you get these little heartbeat blips in the discharge record reflecting these temporary blockages of the meltwater channel. But just getting back to one of the key points I made before, and essentially repeating it because it's so important, I really want to emphasize this. Throughout this module, we've focused a lot on what's happening at the bed of the glacier in all sorts of different contexts, whether we're talking about ice dynamics or the formation of basal ice, or as we move on now and talk about glacial geomorphology, that ice-bed interaction is a really important aspect of everything to do with what we're talking about throughout this module. So I just wanted to repeat and put these pictures, these particular pictures and comments back up here again to remind you that if you're doing some follow-up reading on this, these are the issues to maybe pick up particularly. So talking about water at the glacier bed, what we've said is that water flows at the bed and can be stored at the bed, whether it's flowing or, on the other hand, if it's being held up and stored. Well, that's a major control on various aspects of ice dynamics, but water at the bed in general has a major impact on ice dynamics, and you know that from what we've talked about long ago in this module when we were thinking about how glaciers move, the mechanisms of motion, sliding, resistance, subglacial deformation, etc. Water at the glacier bed is really important in glacier systems. And water at the glacier bed can occur in a variety of different forms, ranging from a basal water film all the way through to Nyand-Rottlisberger channels and linked cavity networks that we've talked about in the context of glacier surging. So this slide, this comment is really just to reiterate that point, that if you're wondering what to pull out and say, here's a big thing that I've learned about, here's a big thing that really matters, here's a big thing that I need to be clear on in understanding how glaciers and glacial geomorphology all hang together, water at the glacier bed. And take that idea and tie it back to the last big ideas we covered, which was the basal thermal regime. Water at the bed and the basal thermal regime, really important, and really important in combination. Also, still following up this reminder and summary of key points, if you like, also I've mentioned the seasonal evolution of the basal drainage network. We've talked previously about how seasons are different in glacial environments. Winter season, the river's all frozen up, the glaciers doing different things, the lakes are doing different things. Summer season, you've got meltwater flowing, you've got meltwater being produced, going into the glacier, flowing through the glacier. So remember this idea of seasonal evolution and tag it on to your idea of long-term evolution of glacier dynamics related to changes in drainage efficiency and subglacial water pressure. For example, remember we talked about surging, we talked about binge purge oscillations of ice sheets. We'll also just think on a seasonal level how what's going on with water at the glacier bed varies through the seasons, and how the lack of water flowing through channels at the bed, for example, in the winter, can lead to those tunnels closing up. And if the tunnels are closing up, if the tunnels are getting smaller during the winter, let alone if they're disappearing completely, but if they're closing down during the winter, then in spring, when lots of meltwater is being produced, where's that meltwater going to go? The tunnels are smaller, so what's that going to do to the pressure, the water pressure in those tunnels or in the glacier bed water system? So high basal water pressure is likely at certain times of year. So if you were thinking of a traditional hard bed surge mechanism, what time of year would you expect basal water pressures to be particularly high, and therefore for surges to be kicking off? And go back and have a look at the records of when surges typically have kicked off in a lot of these glaciers, and it'll just give you an insight into some of the approaches to the research, some of the research questions that people have been asking and have been investigating when they've been thinking about glacier surges. Or it's just a nice little little mind experiment for you to think about when would you expect during the course of a year for basal water pressure to be highest, thinking about tunnels opening in response to pressure from the water, closing in response to overburden pressure, and how the amount of meltwater in a system is going to change through the course of a year. Just something for you to think about as you're doing your background reading to these sessions. And this is it's a very obvious question, but as I always say, sometimes the obvious questions, the simple questions, the big questions are the most important ones. How does the presence or absence of water at the bed of a glacier affect the glacier's behavior? You really need to be clear on that before you move on from this section of the module where we've been talking about glacier dynamics, glacier hydrology, thermal regime, and so on. We're going to move on soon to be talking more about geomorphology, but this is a question for you just to make sure that you really are comfortable with and confident about. How does the presence or absence of water at the glacier bed affect glacier behavior? So I'll leave you to think about that one after we finish this session. So drawing to a close on this first video, there's going to be another video about glacier meltwater, but drawing to a close on this first video, the key points we've made so far is that glacier meltwater is related to the thermal regime. Whether you've got water in glaciers, where the water is, what the water is doing, well, it depends partly on temperatures. Water in the glacier system is very important in influencing and controlling glacier behavior. Also, I haven't said a lot about this, but it's something that you can think about after the session. Water in glaciers tells us something about the glacier. Now, I have said something about that in the sense of the presence or absence of water, and looking at water coming out from underneath the glacier, it can tell us something about the thermal regime in the glacier and the properties of the drainage network, if you are or aren't getting water coming through. And you remember when we were talking about glacier surging, one of the clues to the surge mechanism was the turbidity of the water that was emerging from the glacier before, during and after the surge, and that was telling us something about whether the water had been close to the bed or not, picking up debris, and also whether it had been stored for a long time or not stored for so long. But also, as we move on next time and talk about glacier meltwater, we'll make the point that the chemistry of water emerging from a glacier, that also can tell us about processes that are going on inside the glacier. So that's what we're going to move on to in the next video. We're going to look at how water is important, not just in glacier dynamics, which we've kind of touched on in glacier morphology, but it's also important in sediment transfer and glacial geomorphic processes. So in the next video, we'll look a little bit more at not so much water within glaciers, but meltwater as it emerges from glaciers. And we'll do that next time.